Hey everyone, my name is Good. Thanks for the intro. So here's a video of CSAIL. I guess this is going to be the main theme of this talk. I debated whether I want to talk about reinforcement learning, like locomotion or graphics techniques for robotics. I decided that maybe we'll just try to look at some pretty pictures together. Okay, cool. So today I'm going to talk about. Okay, I should probably post this. Cool. I'm going to talk about feature fields for robotics, language grounded perception and mapping on multiple different scales. Okay, so before I start, I want to kind of motivate this talk by the following example. So one of the things I care the most about is generalization. So what does it mean to be working on generalization? I want to first motivate with this question. If you look at Amazon and I ask you how many different products do you think Amazon has? They call it SKUs or stock keeping units. So if you just go to Google or go to ChatGPT, the number you get is about 12 million. So they have about 12 million different products. But then those 12 million objects actually don't include all of the products from the third-party sellers, and there's about 1 million of them. If you include all of the products from the third-party sellers, this number goes up to about 350 million. Now, this kind of scale necessitates automation. And indeed, if you look into their entire logistic chain, this is what you see. You see automation, but then if you just focus a little bit deeper, you see these people also involved as a critical part of this entire system. So there's still a lot of robotic tasks that needs to be done by people. So I want to look at this particular task as an example. So this task, this person's job is called a picker. So his job is to read the order manifest here on the screen, and then try to figure out which QB the object, the product is in, and then try to place that object, try to fetch the object from QB and place into these order fulfilling needs. This is actually one of the more cognitively expensive tasks. That's why people like it, because it's more fun. And trying to figure out which qubit is the product's in is actually not a trivial thing. So they actually build this augmented reality system where for a given order, there's a overhead projector that tries to highlight the correct bin. And then the person will go into this bin. You see this flashing light and try to fetch the object from usually behind other objects. So Amazon store all of their products randomly to maximize space utilization. So if you look at what this person does, besides trying to figure out where to pick it from and where to put it, he also needs to use his hand to actually feel his way around to try to figure out which object. And sometimes he picks the wrong object. When he take it out, you see that it's the wrong object. He put it back. So this person can pick about 300 to 350 objects per hour. So this is just kind of the going rate for each one of these people. But now if you compare to how many objects this person can pick within an hour or within the work week to how many different products Amazon has, in order for this person to actually go through all of the different products, it's going to take about 400 years. So this person probably has never seen any of these objects that he's picking right now. And despite of that, he's still able to do these a very complicated motor control and a cognitive a task to actually figure out what is the right thing to actually pick and then place into the right bin. So I want to build robots that can do this type of things in the future. And to solve this, I want to focus on solving generalization. And in particular, I care about open-ended generalization. So you can think about this talk as ingredients of open-ended generalization for robots. Cool. So let's come back to this picking task. So why is this task hard? So now we have ChatGPT, we have Midjourney, all of these image generation models. They're very capable. You can give it a very simple prompt, and Midjourney can give you a beautiful picture. I think the thing that makes robotics particularly hard are two things. The first thing is that the robot needs to be able to understand the world through its sensory inputs. So there's perception. And the second part that's even more difficult is that there's this limitless like a number of like a motor skills that like robots or actually like people, animals like need to be able to like know how to do. And all of these motor skills involves interacting with the physical world through physical contact. So I've spent some time like working on both of these. I think today I'm probably mostly going to focus on the perception side of things. If we have time, I can show some like interesting videos of the work I've done like recently on like local motion. But like the bulk of the talk is going to be focusing on trying to figure out a way to build perception and scene representations for robots that enables this type of open-ended generalization. Cool. So let's talk about perception. Here's William. So here he's trying to set up this tabletop scene. We couldn't really build an entire warehouse, so this is the best we can do. What we did was that like we found all of these random objects from the second floor of Stata, and then we just put them into a bin and then like try to place like some of them without cherry picking the object onto the tabletop. You might have noticed this object. This is actually the same Baymax toy from the dense object net paper from like Russ's lab. So our goal is to try to build a robotic system, and in particular, try to figure out like what kind of scene representation that will enable this robot to be able to pick up any of these objects on this table, given like very few examples. Cool. So I want to first show you the demo of like what robots are actually capable of doing. So here we type in like a little text query to the robot, say, hey, can you pick up the Baymax? For people who are not familiar with it, Baymax is this like a like a robot character from Hero 6. I don't know if I get the name right. It's a very cute character. Cool. And the robot like sees this query, and then it, before executing the task, the robot has already scanned the scene, so it knows like where everything is, and then picks it up and put it into the bin. So what makes this special is that we have never seen an example of Baymax to this robot before. In fact, like the closest example I've given the robot so far, that's similar to like a fluffy toy, is this caterpillar toy. And this is also an object from the dense object net paper. It's an exact same object. So how is it possible that our robot is able to use this example to generalize to this example without actually knowing that this is going to be the object we want the robot to pick up at testing? So this talk is going to explain how we figure out like a way to do this with a good level of success. Cool. So before I start, I want to like first just go over like some of these objects. So like we have Baymax. This is all the distribution object the robot has never seen before in the demonstration set. We have this like a blue bowl, and then we have like these two screwdrivers with different colors. We prop it up just so that it's a little bit easier to like grasp it using like these grippers, and also like wanted to show that like we're able to grasp objects with the random like orientation, random object poses. And then finally, there's like transparent jog hidden behind the scene, and if you don't pay attention, you probably wouldn't even be able to see this object in there. Cool. So we're trying to build like scene representation that enables this kind of open-ended generalization. And now if you look at like under vision, I think it was Mar said vision is about knowing like what is where, right? So a good scene representation for robots needs to tell it like what is in the scene, which means that it needs to contain semantic information of the objects and the background. And it also, like, in order for me to know how to pick up an object, I also need to know where to pick up and like where the object is. And this means that I also need to understand geometry. So far, these like large vision and vision language foundation models has gotten very good at telling like what is in the scene. But what's missing from these models that's primarily trained to like learn from and process two-dimensional image data is that they don't really explicitly incorporate like 3D geometry. So even if I can give the robot like a 2D image, and the robot can have a feature map that represents like the semantic feature of like every single like pixel, I still don't know like where I should be placing my my gripper, especially like if I want to do something like this, if I want to grasp like this very thin structure, like with a monocular camera, I wouldn't be able to see like if I'm aligned or not. This actually happens when you try to label these like demonstrations on your computer screen. So I built like a whole suite of open source software that allows you to actually do everything that I can do like in the web browser, but also in with the VR and AR like headset, and it's open source. It's called Viewer. I'm going to show like a little demo like at the end. Cool. So we know that like the scene representation of the robot needs, you have both semantics and geometry. And we know that the semantics are already quite good with these foundation models. What can we do? So this work I'm presenting is called distilled feature fields enable few-shot language guided manipulation. Cool. So our idea is that like the semantic feature from these foundation models are trained primarily on like two-dimensional images already quite good, but they lack the 3D geometry. So you can take, just to explain the input and output spec of these models a little bit, so that like we're not jumping into too quickly. Here's the image of the scene in front of the robot. I can pass one of these images through like a vision model or like the vision part of a vision language model, and then I can extract these two-dimensional feature maps. Even though like the features here are very rich, it doesn't really tell me like where I can grasp things specifically in 3D geometry, and this is a 3D scene from which this model is taken, like this image is taken. Sorry. Even if I know this,
to be clear, the feature map, is that just like some latent representation partway through processing? Like, where does that come from?
Oh, I see. I'm going to explain a little bit more on this, but if you look at like a clip,
yeah,
clip is actually like trained to actually learn to model like a bag of words. So it behaves like a bag of words, but it's trained that way. Also, it's trained to be an image level feature. So we know that from like other work in transformers, right? You can actually extract like features from the penultimate layer and then like use those features as like a 2D dense feature. But the problem with these vision language model is that if you do that, not from like the image level feature, you actually destroy the alignment between the language branch and the image branch. So we did something clever here. We looked at the parameterization of the last layer, and then we just like stripped some of the components out, and then like kept some of the components, and then we managed to actually extract like a dense visual features from clip without destroying the alignment between the vision side and the language side. And it only took us 24 hours to actually like from start to finish. So what we do here is actually extract like these like dense features from clip. It's pretty different from what people have been doing in the past, because like if you look at LSEG or like a lot of other work, right? They take a clip network and then they get rid of the last layer and then they try to like train it. So the idea of like this project really is the way towards robustness and generalization is through like the data and the data kitchen sink that can absorb all of these data, plus like the necessary like inductive biases. So we didn't want to do anything that actually we didn't want to do anything extra. We just wanted to see like how well these features externalize like out of the box. So that's why we did this. And it turned out there's a paper that actually figured out how to do this like 2 years before we did this. But it was kind of stuck in like submission and didn't get accepted until like early late. It was initially called like dense clip, and then like someone took that name, so they changed the name to like a mask clip. So now this is called a mask clip. Yeah. Cool. So knowing this doesn't tell me how to grasp here. Okay, so what can we do? So we have the state of the art like visual features, right? And if you look at the state of the art like methods for representing geometry, you have NERF, and now you have Gaussian splatting. So why can't we combine these two, and then try to have some kind of like scene representation that actually like has the property of both? Is that simultaneously being able to capture the semantics, but also being able to recover highly detailed 3D geometry. And this turned out to be the distilled feature fields. So distilled feature fields, or like 3D feature fields, were initially developed by the graphics community to enable like scene editing. So the idea is that like these 2D vision features contain a lot of like priors on objects and their semantic properties. For example, like if I'm looking at this phone, right? Like the concept of a human phone didn't exist before like a human civilization. So this is something uniquely like human, right? But these models actually know that. So the idea is that maybe we can use these feature fields that graphics folks develop to enable editing for robotics applications. So like we couldn't come up with a better name, so we end up just naming a feature fields for robotic manipulation or a firm with a nice animation. Anyways, so firm has like two main parts. The first part is how to actually produce this type of 3D feature fields in the robotic setting. And the second part is how to actually use it for manipulation, in particular language guided manipulation. So the way that we produce these feature fields is the following. So here on the right, we have a little mount made of aluminum with some magnetic attached to it, so that the robot can pick up this a selfie stick with a real sense mounted at the end. This is basically the first object we built for this project, and it's probably easier to have 6 or 7 camera mounted around, but we got stuck with that. So be careful what you try to do at the beginning. So the robot picks it up, scans the scene like 50 images, and then using these 50 post images, we can train a nerve. So here's the nerve produced using those images. Go back. There you go. Yeah. So this is a nervous scene. So all of the pictures you have seen so far, except the video, are rendered. Okay. So you notice that the geometric reconstruction is very good, even though these are transparent materials, but it still has some problem with the reflective materials. Cool. So what we do differently from standard nerve is that in addition to try to reconstruct the geometry and the appearance of the camera views, we also pass each one of these images through the Clip Vision module, and then we extract these dense 2D features from each one of these images. And then in addition to render the RGB color values of each one of the pixels, what you can also do is that you can simultaneously try to render these two-dimensional feature maps, which is much lower resolution than the RGB images. And this is what we get at the end. So this is a Dino feature field, even though I was saying the clip earlier, but Dino has better colors. I'm gonna show a clip feature field in a bit. So what you notice is that geometrically, we get very nice reconstruction. You see all of these very thin structure. You can see this piece of leaf we put on that's attached to the grape. It's fake grape, but the banana is real. And then you also see that there's a very nice boundary in terms of semantics between the objects and their backgrounds. You can see these different colors. So what I'm showing here, the RGB colors corresponds to the 3 principal components of the features. So this is the representation that the robot sees.
So did you just replace the color with the features in the optimization? How did you do that? Tell us a little more, how did you do that? Did you replace just the RGB with the color or in the optimization?
Okay, so we treat photometric a part of the scene of this process very differently from the feature side. We only use the loss from the RGB reconstruction to learn the geometry, and this is something that we're going to see with the generalizable feature field as well. Is that photometric loss offers you the best geometric reconstruction. And then the way that nerve renders, I'm sure you know about. I'll go over this. The way that a nerve renders these viewing angle dependent colors is by encoding the colors using spherical harmonics, right? And the Gaussian spline does the same thing. But we assume that the features are actually view agnostic or view invariant. The idea is no matter which view angle I'm looking at this, the table is always going to be a table. So that's the assumption we're making.
So is it?
It's not necessarily true. And well, it depends. So what you see with the clip features is that the features from different angles do look very different, and it shows up in the distilled feature field. This is less a problem for these nerve-based feature fields, but for 3D Gaussian splatting, because the 3D Gaussians tend to be able to fit to high frequency the noise much better. You see a lot of sparkles, and they'll show up in the scene when you try to do the composition of these features.
But what do you do at the end? Do you average or what do you do? I mean, a point in 3D is projected from the pixels. And I have for every pixel, I have a time of whatever feature. Are you averaging all of them?
I see. So like my mental model for like what we do with the these with this way of distilling like the 2D features into like a feature field is that it's merely doing like some kind of like a counting or averaging between multiple different views. So it's like pretty cool if you think about it. Yeah. And we do notice that the features are very different from different angles.
You said you did this with Dino. Does that also hold with Dino? That they're very different from different views?
Dino actually works. That's a good question. So Dino actually works much better in terms of like from different views and I don't know if you folks noticed. So like the Dino features behave very differently from Clip features. So Clip gives you much better like separation in the feature space on the sort of like property and like object category level. So if you look at the Clip feature, like you can tell like this banana different from the orange juice, even though the two colors are pretty similar. They're also similar because like they have similar colors and like Clip overfits to color. And then like if you look at Dino, what's really special about Dino is that like a Dino offers you like an incredible part level dense correspondence. So this is like actually like the original reason why we started this project. We started this project because we look at dense object net, which uses correspondence in 3D to train like the 2D dense descriptors. So the pipelines, I have like 3D data. I know like how like these two patches corresponds to the same like point in 3D. Therefore, the representation for these two patches need to be similar. And then for all of the other points, it need to be different. And if you look at like ways that people learn dense descriptors, it's always been the case. And we look at like the Dino paper and the analysis, and it's like, wait a second, but you can get like incredible dense correspondence by just training on like large amount of data using self-supervision. And I don't know if you folks have seen like the result, like the original like the Dino analysis paper shows that if I have like a cat and like a person and like some kind of like other animal, the feature that corresponds to like same area of the face actually like are highly similar. So you get like part level dense correspondence. So the experiments we try to do is like Baymax is a featureless object. So like there was this very beautiful like a dense like a beautiful description like an image from like the dense object net paper that shows like at different like locations on this like featureless object you have like these different kind of features, right? So we were able to see the same thing, except when the picture is saturated, it completely throws the transformer off because like all of the pixels are like the same color. So we learned to take better pictures with this.
So would that same concept like affect you with synthetic images versus like real images?
So
like say synthetic as in like you don't have the kind of shading differences, but like each face is like the same color.
I see. Okay, so the question is like if I have like synthetic image where the face is actually cartoonish with the same color, is it going to affect things? I'm not so sure because the type of saturation I'm seeing here is things are just completely white.
Oh, okay.
So it's not like there's a color and then there's a boundary. Yeah, but that's a good question. Cool. Any more questions, everyone?
Are these features robust to like multiple copies of the same object? Let's say you have two Baymaxes in the same scene. Does it give you the correct correspondence?
I see. So I wasn't sure about question, but like we try to buy like Baymaxes of different sizes, and like the dense correspondence like it does like work to some extent. So we have like a big Baymax, we have like a bigger Baymax, and we have like small Baymax. It's like the tabletop like collectibles. Yeah, but it's definitely not perfect. Yeah.
I have another question about how like detail
Mm-hmm.
spatial geometrically this feature you can describe. For example, if I say the left hand of the point or the right hand of the point and distinguish between this kind of fine-grained geometric detail.
I see. I don't recall on top of my head how like the data augmentation was done with Clip, so it depends. If I recall correctly, I think Clip actually uses like a data augmentation to flip the like.
But I mean, really, our experience told us that, for example, Dino cannot distinguish this. Like one click like hand, or left hand. During the right hand, it also like has very high similarity.
Mm-hmm.
I don't know how this kind of like like mid-level semantic, but that the manipulation or like some maybe if the task really involve local like action, they're really dependent on small structures, what happens?
Yeah, like I don't think like Clip can do that, and it's not surprising that NL cannot do that. And then the question is, so I'm actually not trained as a computer vision person. So like as like I try to read like Dimar's book, I still don't have like an intuitive understanding like of like what the whole feature means. My intuitive understanding is like something like kind of like well I'm not going to say it, but like I don't have a good intuition of like what it means. Yeah. Happy to check. Okay, cool. So anyone is everyone like ready for robotics? Okay, cool. Okay, so this paper is like half like vision, half like graphics, or mostly graphics and like robotics. Okay, cool. So we're talking about like a representation for the scene, right? But when it comes to like a learning to control or learning to make decisions, you're not necessarily trying to like represent the scene per se or trying to represent behaviors. So the object we're trying to represent is not like the scene anymore. So how do we represent these demonstrators we collect from people? Let's take this training object, for example. So the way that I want to represent this behavior is by representing the 6 degrees of freedom grasp by its relationship with the scene. So I represent like demonstrations by its relationship with the scene itself. So the way that I do that is I sample like these query points in the canonical frame of this gripper. So when I rotate this gripper, these like randomly sampled points rotate together with it. So we only sample these points once, like at the beginning when we try to collect data, and we don't change it for all of the demonstrations for the same kind of task. And then we try to scan the scene to extract the feature field of this test object. And then we can represent this demonstration by assembling a representation vector from the feature that's sampled at each one of these points in the query point cloud. So the way that we enable this kind of like a distance, like an interaction or a relationship at a distance, is that we anchor this point cloud in the canonical frame that transforms together with the gripper, but we allow these query point cloud to actually be displaced and to be placed at like off the physical like geometry of the gripper itself. So this is how we manage to model like a relationship over like a certain like distance. You know what I mean? Questions?
Is this the image itself? So you see the gripper? Is the image itself? You see the gripper?
We don't.
Where is the camera?
So basically this is a feature field, it's a 3D model of the scene. The camera is mounted on the selfie stick. At the beginning of this session, the robot pick up the selfie stick, do a scan and collect like 50 images. And then we do a structural motion for all of the images to get like the camera poses. And that allows us to produce this feature field. So the robot scans once, builds this model, and then like
that was clear. But when you say demonstration, there is something the robot does something.
Oh, I see. Okay. Okay.
So is this visible in the campaign? Like what we see the actual image, or is it an abstraction?
This is the actual data, by the way. We put a lot of effort into these visualizations. We actually built our own rendering pipeline and also our own like a virtual reality environment. So this is actually done on the Oculus Quest in VR. Yeah, so like we had a lot of people did like it was like people were asking us like why do you spend so much time writing like web apps? This was done like over just like a minute or two, like just quickly do it like 2 demonstrations per object because you're wearing like a headset. So you can actually like lean and then like try to pose the gripper like really precisely in VR. You can see it right here. Yeah. So we do that using a point cloud approximation of the feature field.
My impression is that you would like to calculate some correlation for the points that are near the gripper and the 3D feature field of the object.
Mhm.
So why are the points not on the gripper? I did not.
Oh, I see, I see. Yeah, so, okay. Okay. So the idea is that, there are many kind of like things I want to do, that involves like me positioning myself like with respect to some kind of like a structure in the scene, but don't necessarily, be in direct physical contact. So I want to be able to enable, I want to be able to model like my behavior by a relationship that happens like over like certain distance. I need a good example. Any examples? Oh yeah, that's right. Yeah. Okay. Okay. So here, you know that this should be like roughly somewhere in between the two like fronts, because we know that this is actually the point of contact. But then what if I'm trying to use a hammer? Like the hammer doesn't have these two things, right? For tool using. So, and then you intuitively know that like the point to focus on is actually like at the tip, right? That's because we know. So, but the robot doesn't necessarily know that. So like in this case, we're helping the robot a little bit by saying that, okay, for this particular task, let's just like a sample, like a very large blob around like this area. And then we're going to like either like optimize the location of these points, or I can just like tune the like parameter of the Gaussian a little bit so that actually overlaps with the part of the object that I'm interested in. So this is kind of like it involves like our human priors. So the idea here is I want to represent this thing in the context of the local like feature field. And the way that I represent the local context for this particular pose is through this discrete representation. So like the location of the feature points in the feature point cloud in the canonical frame of the gripper, together with the features that they carry, forms like a joint representation for this pose. And it's representing the pose in the context of the local like scene field. Yeah. So
Right.
yeah.
Just ask for the hammer example, are you saying like some of those points should be sufficiently far away from the gripper so that you could learn to grasp the handle of the hammer by knowing something about the head of the hammer? Is that what you're saying?
Yeah, like I'm kind of blanking out a little bit. Like I had like there was a very clear reason why I did that. I remember. Okay. So imagine you're trying to grasp like a mug, right? So like you think you're grasping the handle, but you're really grasping the hole in the handle. Like how would you actually model the hole in the handle without being able to model like a relationship over distance? Yeah, so that was actually the idea. So like many times like I'm gonna try to do like so kind of like threading a needle. Yeah. So I want some like you can think about this as basically a 3D version of convolutional network, right? It is basically a ConvNet, except that we're not learning the ways, but we could. Yeah.
Did it have to be random because you've done a regular career? It's just adversarially robust.
It doesn't have to be random, and like random is probably pretty good, but it's definitely like there are definitely better ways to do it. Like so, for example, if you look at like graphics work, the way that they sample like points around like one of the like Arabians, there's a lot of like there's a lot of like a thought that goes into that. Like basically, you can prove that like for like 7 points, this is the most optimal way to actually sample like around. Yeah. Cool. Any more questions? All right, so now I have this representation for the demonstration, right? Like how are we going to do like incorporate language guidance? So this part is a little bit involved. At test time, the users say, hey, can you pick up a blue ball? And remember the blue ball from earlier, right? We first pass this like a text query through the text embedding of the clip model. And this gives us this blue embedding of the text query. Now using this text feature, I can look through all of my like demonstrations in the small set of demonstrations I collected earlier. So here's a demonstration over the Caterpillar toy, and here's a demonstration over the like a very large drinking vessel that's about the same size as this camera. And then like here's a demonstration over one of the screwdrivers. It's a yellow screwdriver. So we only have like 4 object categories and 10 demonstrations in total for this entire paper. And the first step is to use this to select the most appropriate demonstration. In this case, what's really interesting is that even though I'm asking for the ball, the demonstration that's being selected is this demonstration over this water a water beaker. So now using this a demonstration retreat in the first stage, I can try to scan through the entire scene in the 6 degrees of freedom configuration space to try to figure out the grasping poses that are the most similar to the representation we have from this particular demonstration. Now, this is the actual result. This is actually result of optimization used in the video. So you see these are the top 10 grasping poses, and they're all concentrated on this edge of the blue ball. So we do actually have proposals around this edge, but we reject anything that will actually have physical a collision with the table. So that's why they're on the top. What's interesting here are 2 things. The first thing is we're kind of using these human demonstrations as a task agnostic or kind of object agnostic grasp prior. So a data we're just using a data points to represent what are the type of grasps we would like the robot to perform, because we don't know what exactly object we want the robot to grasp at test time, right? So this is my grasping prior, and this object that's being used here is different from what is being asked. And in fact, if you look at the scene behind this blue ball, which is the target object, there are actually these 2 drinking beakers from the same object category, but the robot's able to ignore them. So now, let's see.
How did your optimization actually take those? Right, you matched with the language, but then and it had other suggestions of things around it. But did you start with random initializations across the entire scene and then solve most of them?
Yeah. So I feel that'll be better explained as part of the example. I have that problem with this part of talk all the time, because you need to be able to see the scene. Okay, cool. Let's just look at an example, and I'll walk you through step by step, on the actual example. Okay, cool. So here's the result. Let's go back to the Baymax example I had earlier. So here's the nerve we built for the scene, so the rendering, and promised. Here's the clip feature field. You can see that clip feature field they look very different from the dyno feature fields. You do see these different the features correspond to different objects, but you don't really see part level structure. Cool. For this entire for this entire experiment, the only demonstration I use are these 4. So we have 2 different ways to grasp a 1 red mug and a blue mug. We have 2 demonstrations over 2 screwdrivers. We have 2 grasps on the same category toy, and we have 2 place demonstrations on this particular a rack, drawing rack. Cool. So I'm going to show first generalizing to novel objects that a robot has never seen before, and then I'm going to show you how the robot is able to tell objects you want to pick from the objects you don't want to pick by appearance, and also by physical properties. So let's talk about that first. So here's Baymax. Now what you see is this RGB image from the camera, but what the robot sees is actually this heat map. So we can very easily try to render the attention map by just calculating the cosine similarity between the text query and features on the scene. So to answer your question, this is actually the first step. So we first use this to try to find locations we should actually be running optimization, and that basically means filtering out most of the rest of the scene except this Baymax. So that's why using the text query we're able to isolate the blue ball and ignore things in the background.
What do you mean clear out the distribution in the grasp demonstration and don't the grasp pose for that?
No, we don't. Yeah. So the demonstration that's used to actually pick this Baymax up is the caliper toy. It looks pretty different. But yeah. But clearly the clip model has seen a Baymax before. Yeah. Okay, cool. And then we can tell things apart by their appearances, differences in their appearances. So I can say, hey, can you pick up the blue screwdriver? So there are 2 here. There's 1 red and 1 blue. Now, even though you see colors, the robot sees the T map. So the robot knows that this is the one that I should be paying attention to. One thing that we notice is that clip actually overfits to color a lot more in the object category. So sometimes you have a yellow toy and an orange juice or something like that. and you say, can you pick up the like the orange toy, and then it picks the orange juice for you instead. So like we solved this problem by actually offering like a negative queries to actually filter out things we don't want. And we noticed is that like once the human users start to use this, they start using negative queries to actually like modify the robot's behavior in form of prompting, which is interesting. Cool. And now we also have this like red screwdriver, but before that, we're going to try to pick up another object. So transparent jug. So this is actually my favorite example, because if you just look at this picture, you wouldn't actually be able to see where the transparent jug is. But then if you look at the heat map from the robot knows that that's actually a transparent object, and this is what's being lit up. And then the robot figure out the pose, and these are the demos being used to try to compute the grasping pose.
Sorry, again, how are you generating the heat map over the internet?
I see. So like the NERF model is able to like render like output two things. It's able to like output the RGB color values at each one of the locations. That's how the NERF like renders like null views, right? The NERF model also has like another like output head directly renders like a high dimensional feature. So one thing that distinguishes like a feature fields from like a prior work that uses kind of like point cloud to carry like these features is that because this compresses things using like a neural network, using like a feature grid, like plus a neural network head, we're able to accommodate like a very high dimensional features. And you're going to see like why this is important like in a bit. We're going to try to scale this up to like a much larger scenes and like high dimensional features. We're able to accommodate like 1400 like without any problem. It's the same like model size.
I guess what I mean is like, you have to sample a bunch of spatial variety points and then like measure this and then in your text input and the like feature.
I see. What we basically do that is render the image. So like we render like because we assume that the features are like invariant, right? So we can just render the features, and then we take this like very thick, very big like a feature map that's actually like a pixel dense, and then we just run full sense similarity. Okay. Yeah. Cool. Yeah. So like we try to like figure out ways to enable open-ended generalization. And the limitations, this is actually the fun part. So like the robotic experiments was extremely painful. Each one of these like scans takes about like 2 minutes, and then like 9 seconds for the optimization. We do have a very fast like a NERF and like a feature field reconstruction like pipeline, but still like we probably should have like use like multiple different cameras as opposed to like a cute little selfie stick to actually do the scan. What's nice about like this setup is that like the robot has a much larger like working area. So like if you look at like this versus the work that uses the wrist mounted camera, like the wrist mounted camera has like a very limited workspace. So like you can't really scan like a big scene like this. So that's the first thing. And then like being NERF, like we require dense view coverage, and we don't really translate any knowledge of the geometry aspect of the scene understanding like between like scenes or like from like a data sets with optimization for scene. And then I shouldn't have said like clip behave like a bag of words, because clip is trained as a bag of words. You don't really have like a perfect behavior. So you have like confusing factors, for example, color, texture versus like object categories that I care about. But because we can use negative query words to filter out properties I don't care about on the fly. So you can think about the positive text queries and negative text queries both as part of your specification for a task. So in practice, it actually works well. Questions? Cool. All right. So so that was that. We managed to basically build like a scene representation for a tabletop scenario, and then we decided to have a little bit of fun. So can we scale this up? So this is our rendering pipeline. This is like this is running in the browser, and this is the actual like a 3D scene. So you're going to see that like if I zoom out, I can actually see the rest of the second floor CSAIL. Now, here's actually a model that does that. So like here's the table. This is one of the white tables on the second floor near the embodied intelligence common area. Now, if you zoom out and look at the entire model, this is actually like the kind of scene that this model is able to capture. So the same pipeline we use to model the tabletop scene that we use to actually do accommodate language queries for isolating objects and like also works for much larger scenes without any modification to the pipeline. So here we can see the chairs, and now I'm going to start like acquiring like this with different context prompts. You can think of this as a live demo for the just a scene representation part of the project. So here I say, can you actually find me all of the lamps? And this is what you see in the scene. So you can see all of the lamps like being lit up. I'm only going to show this video, but like if you ask for railings or stairs, and then say, hey, I don't want to pay attention to like stairs, I just want to look at the railings, we can resolve like individual like bars of the handrail. Cool. This is my third example. So like I just did this, this is actually the first video I made of this like viewer working. So I said, can you find me a trash can? You wouldn't probably even be able to see that there's a trash can here, like because it's so occluded by the stairway. But because we have a 3D model of the scene, that actually carries the feature vectors. I can do this kind of like open vocabulary, like search in this field. So this is a search engine for the 3D space. So now, like,
How does this compare to OpenSea now? Yes. That's exactly the same.
we got sued.
No, early like in 3PR, last this year in 3PR and early this year, that several people in 3D vision community doing this stuff.
Yeah.
Yeah.
We got sued. Like we're too slow. Like basically like this project has been like already doing robotics project or doing like vision project, and we're all going back and forth. Yeah. And also like another thing like with overseas is that like if you look at like is it habitat data set and like replica, like if you look at those data sets, like you can try to run NERF with modeling on those, and then realize that like those like data sets are really not designed for like training NERFs. Their reconstruction is not very good. You also notice that like the human pose is often like wrong. Yeah, so like we couldn't really figure out like a good like a large scale data set to actually try to do this. So that's why we're actually collecting our own data.
How many images do you use of this room?
It's 1 minute and 40 seconds. So that's about 200 images. So we do it's like 200 to 300 images. We actually don't want a lot of images. Yeah, it's like a 1 minute 40 seconds.
I'm curious because like the top of the lamps was also pretty well visible. So where do you have a rough understanding of where you take the pictures?
Yeah. I can tell you. So like let's see if I can. Okay. I basically my trajectory was like this. I went like that, and then I went between that, and then like I came back like that. That's my trajectory. So like the trajectory is kind of like it's kind of like that.
And I'm sorry, I missed the first part of the talk, but this is Gaussian splatting to build the 3D.
This is a feature field. I'm going to show a live demo of like a Gaussian splatting, like running the browser. Yeah. So like so okay, this works well. Like a model's small, like you can actually compress like 3D data because like like you can't really compress like a 3D point cloud data very well, like before NERF, right? Like you don't have JPEG for 3D point cloud data. That's why like those data sets are so big. But yeah, like we actually have something that we can use to actually model larger scenes. And besides just modeling like RGB like appearance, we can actually also model the semantics, and we can do search, right? This is pretty fun. Okay, so we figure out we can do that, and we can find trash cans. Like the geometry is really pretty good. So can we actually use this to build like a map? This is like a fun like a summer project. It's a project called like a Beantown. But before I get into the map part, let's actually first show you like the kind of graphic stuff I did for fun. So because I have the 3D geometry, I can extract like high maps like out of the NERF scene, and because I'm rendering everything using WebGL like inside the browser, so I can actually do like a relighting. It took me a while to get like surface normal like a calculation to be done correctly using this. But what you see is that like I can actually have actually use this to go like a real to sim and try to like construct simulation environments for a robot. Now, because everything's actually like running like real time, I can actually modify like the parameters. I can change the geometry. In this case, I can connect the geometry to ISACGEM and then try to run the robot like a control policy in the scene. So this is a robot that's trained using reinforcement learning. This browser session is actually connected using WebSocket directly with the Python backend that's running the physics. So this is sort of like where we're going. We're trying to like build like a simulation environments using either like a real data we acquire from like 3D scans or trying to use like generated models to generate like a 3D scenes. So we have a project called Lucid Sim that does that. Cool. Now I just show you how to go, like we're able to go from tabletop to like a kind of entire floor. And the question is, can we actually be more ambitious and like try to capture bigger scenes? We can go from entire floor to entire city. Not quite yet, but here's like the result we got. So like during the summer, we figure out that like using these consumer grade 360 cameras, you can actually get really nice images, especially if you have a highly motivated, very good high school intern. So here's like Alan and Kyle and Kevin like driving this car around. And you're looking from perspective of a 360 camera mounted on top of the car with a 3-meter long carbon fiber stick. And this is the area this is near Central, like on Mass Avenue. So using these two videos of the car driving like on like two directions, we're able to reconstruct like a map like this. So this is like a nerf reconstruction of the scene.
This is all one nerve. You didn't chunk.
Yeah, this is one nerf. Yeah.
Oh, you can see people walk.
Yeah, I see people walking, right? So like over the summer, we try to do like a generative refill, like to actually like infill the people with like a road and stuff like that. We also like built a complete like fully automated pipeline to use the GPS location of these like 360 videos to actually automatically process all of these things. So the tricky bit is that like when you have like a car underneath, you always like have a car underneath. You can't really like get rid of the car underneath that's traveling together with your camera. And also like in traffic, you also have like other cars traveling together with you. So these are the problems we run into. Cool. And so we also took a drone and then like flew around and tried to collect some data. And this is the 3D reconstruction using like a 3-minute long like a drone video flying around data. And the reason why it's 3 minutes is because we couldn't fly faster. We actually don't need that much data. Like as like for people who work with NERSC, you know that like you need about like 3 frames per second, and for a scene like this, just like a minute is enough. So this gives us hope that this is actually a scalable approach to mapping.
Did you use all of the frames you got from those 3 minutes?
No, we didn't.
Okay.
No, we didn't. You can do interesting things with the frames in between. Yeah, like so that's the problem with NERF, is that we throw away the frames in between, but you can actually do things with it. Yeah.
How did you do the localization? Is this all the control map?
Yeah, structural motion. Yeah. And it's kind of funny, right? Because like a code map first builds an internal 3D model, and then you get a camera pose, and then you build another 3D model. It's like still classical. And sometimes, like if you're lucky, you can actually capture like across the river and capture part of Boston. How much time do I have?
3 minutes.
Oh, cool. Perfect timing then. Cool. So like that was using neural fields for perception and mapping. So what have we covered? Like we show that like on tabletop scene, we can use this to enable open-ended generalization or like open like a vocabulary like grasping in place. And then for indoor scenes, we're able to capture fairly large spaces. And for outdoor scenes, we can actually potentially scale this to like much larger like areas like a city. We use this to build like indoor and outdoor maps. So the reason why I'm doing this is because I thought that now these generalist AI systems like ChatGPT and these image generation models are all becoming extraordinarily capable. And the only thing that stops like robot from being able to do that are perception and the requirement to actually know how to interact with the world through like physical contact. So maybe those problems are problems we can actually solve. And if we solve that, all of these robots will require like a new set of infrastructure to support them. So the focus here is, instead of making the robot smarter, we also want to make the environment smarter. So like the thing we're doing with this is actually like building generative search engines, so that we actually have an intelligent system like that's directly attached to the mapping and geolocation data that can actually provide like supportive functionality to the robots. Think about like basically the Uber or Yelp for robots. Here's just like our undergrad researcher, Alan, driving the robot around. And the problem with that robot is that the robot is actually blind. It's being piloted by a student. So is it possible to actually have something like so generalizable and gives you like such a good like 3D like geometric reconstruction running at real time on a embedded system on a mobile robot? So that's one of the questions. And they're very like we'll have like work under submission and also like the rest of the community are working on something like this. And the direction is to like make nerves generalizable and in fact like make generalizable feature fields. And it also means like you probably want to change the kind of sensor you use. For example, like with the single camera, you don't really get like scale invariance. Maybe do like a dual camera setup. So they have like fixed baseline. Maybe like instead of doing two cameras, like two like regular perspective cameras, you probably do like two like Insta360 cameras. They're gonna just get more out of it. And the second thing is, if you think about like a navigation, in self-driving cars versus like what we did with like a grasping tabletop, the representation people use are very different, right? So people use like point clouds in many cases because point cloud generalizes really well. It's just geometry, right? So is it possible to actually like have a single unified representation for all of those things? Now, like also like now we have this like a format to connect like semantic features from pre-trained models to geometry. And that just opens up like a whole world of possibilities. What are the different downstream things we can connect this to? What are the different type of features we can put into this? For example, can we actually generate a text as opposed to just treating the scene as like something you could do like a discriminative task on, like a segmenting part of it. So these are like the things we're thinking about working on now. And the hope is that maybe by building these maps and your generation of simulators, and these like perception, scene, understanding like the technology, maybe we actually have all of the pieces that's needed to actually build robots that can mingle with us and coexist with us in like complex urban environments like this. That's the talk.
Thanks for the great talk. We're technically over time, so if people have to leave, that's fine, but I think there's a few minutes for questions. So if you want to stay and ask a few questions, that's great too.
I might have missed it, but did you run feature maps on the like city scale?
Oh yes, it's like all part of the default pipeline.
Okay, cool.
Yeah.
I had the same question, but I was wondering if like you can reason about semantic features like buildings and things like that scale, or if the data sets are not available for that kind of.
Like what you notice is that scales are not invariant. Like things are very different. For example, if I want to do like object slam, I can like do that well, like because there are all of these like chairs, right? But then like what are the objects like on the city scale? Like the buildings, maybe? Like yeah. But like because like these things are trained over like a large collection of data, so they have seen like the buildings. So they're able to extract very nice. The real problem like using these like 2D feature extraction is actually like a very classic like vision problems, like how to actually capture the context while you're capturing the details, right? Like that has always been there. So we see that like as well. So like if you, I don't know if you remember one of the data sets from WRF, there's a bear like sitting on the right and there's like a sheep on the left, like with Dali in front of it. Okay, so like it's like if you don't do like multi-scale like feature extraction, you can see a bear, but then like a bear has a hole in it because like for those patches in the middle, like it doesn't know that's part of the bear. So this still happens, and it's not like a sole problem, but I think it's okay. Like we'll just work with it. Yeah. Cool. And these are people I've worked with, and Ran is actually doing the like map building effort. It's painstaking. It's very difficult.
What are you doing to make this real time?
Or
I guess online, because that was the next step. So.
Oh yeah, so there are two ways to do it. Like one way is use like something like a pixel nerf that actually operates in the camera frame. So like graphics people know that generalizes a lot better if you look at the original like pixel nerf paper. So one critical thing is that you actually want to separate the geometric priors from like the features. So what you want to do is that if you want the geometric part to actually generalize well, you want to use like these pre-trained features at the front end, and then like learn like a small head for the geometric like association on top of that. So you can think, I mostly think about this as a light field, like a generalizable light field model, because it's about like how do I associate like patches of my rendered view back to like original like context images. And then like when you try to reconstruct these features, you don't actually want that to be distilled into a smaller network because that destroys your ability to generalize. That's actually okay in some situations, but like if you want things to be generalizing out of the box, you want to just use unadulterated like original features. And what you want to do is that you want to actually use the geometric prior as like some kind of attention mechanism. So literally like a light field. These systems run really slow. So you can't really use them on the rest. So like even though like theoretically you're just using 1 or 2 images, sounds good, but it's actually in practice really slow. So how do you actually deal with that? So like one thing you can do is that you don't render images. You just try to extract like a features from the implicit 3D volume. That's one way to go about it. And then the second strategy is to use more explicit representations like a Gaussian splatting. The reason why I like Gaussian splatting is because like it has like a lot of different properties. For example, if you look at like an object slam represents like all of these objects as like Gaussian blobs, right? So Gaussian splatting literally gives you a way to go from a single blob for the entire object to like 1,000, 10,000, whatever, how many number it is, like for the like fine geometry. I feel like that's a like special power you got to like try to take advantage of. And the second thing is if you look at the dense dense lamps like methods, these Gaussians can also correspond to like those features, right? So like, and I think the work just came out yesterday that practically does this, is that they use Gaussian splatting as the like online representation format for like a SLAM system.
And they do bundle adjustments over.
Yeah, that's right. Yeah, so you can do that. Another way is to go sparse, just represent things as like points.
I'm missing something like between the tabletop scenario and the city level. I see you scale out the thing and show. Is that basically show show how you can basically build a very large scale and data, or because you do not do manipulation or language related query of the.
We're able to do that. We're able to do like a language related query. So because Xiaolong gave his talk last week, I didn't want to repeat the projects. You might have noticed that like a bunch of things disappeared. I think he presented the Jeff paper, GEFF, almost like GUN or GUFF or like a Jeff, whatever. So like that paper basically uses generalizable feature field as a unified representation for both navigation and manipulation. So the idea is like, even though these two are very distinct tasks, like in order to actually build like agents that can actually generalize to a lot of things, we need to figure out like ways to build things like in the more generalizable fashion, like in a more general fashion, so that like the one thing can actually be useful for many different things. So that project was that. It's like a single unified representation for 2 very distinct robotic tasks. And then we also have this thing called like feature splatting. So the idea here is we know like an object SLAM system uses like Gaussian blocks to represent like objects, right? But then Gaussians, 3D Gaussians are also really great primitives for like modeling contact physics. So why don't we actually try to just put it like connect it with material point methods, and then try to do like a cloth simulation, try to do like a liquid. So like the demonstration like I showed last week was that like we have this like scene, and then there's a fire hydrant, and then say like I turn the fire hydrant into liquid, and this thing just melts. So like the really nice demo is say, hey, turn the chairs into liquid, the chairs melt. Turn this camera into like they just start to disappear one by one. So that's something we are able to do. So the idea there is feature splatting is a like a unified representation for 3 things. It's a unified representation for modeling geometry and experience and appearance. And it's a representation for semantics because we're able to distill very high dimensional semantic features into every single Gaussian block. And the third, you can use the same primitive without additional collision geometry or geometry for physics to incorporate like physics. So the paper is called language-driven. What was the title again? Language-driven editing of appearance and physics. Or I forgot the title. I can't remember the title, but like I forgot what it is. So basically, the idea is that we can actually jointly edit the appearance of the scene as well as like the physical properties, like material properties, so that we can actually affect the physics. So one of the demos, like I have a piece of cloth. So cloth is easier to image with Gaussian, like because it's thin. And then like an image of cloth, and then like it's a static scene, and then throw a ball at it, and then like the cloth actually behaves like realistically. So that's the idea.
So have you tried scaling up the dimensionality of your feature vector?
Yes. Yeah. So for the like for this one, it's not a problem because it's just the output of like a neural network. For Gaussian splatting, what we did is we look at the like a slowdown. So there's a very significant slowdown when you try to scale up the number of feature dimensions. And we figure out the root of it. The root of this is because for every one of the 16 by 16 like image tiles, all of the gradients are being written to the same CUDA DRAM slot. So you have like a 256 memory queries that's trying to like go through this like a single like a bottleneck for like in the single like DRAM slot. So what we did was that we wrote additional like a pixel aligned gradient buffer in the L1 cache of the GPU. And that allows us to actually have the gradient updates being interleaved. Interleaved means every single pixel will be writing simultaneously to a different slot in that like a gradient buffer, and also like the buffers in the L1 cache. So it doesn't have to like wait for like the week of travel to like the DRAM. So we have a state-of-the-art feature splatting implementation that we plan to open source. And the reason why it's state-of-the-art is because we did these kind of system engineering to make it happen. If you look at existing methods for either like feature splatting or for either like feature field, a lot of times people do like low rank approximation or people do quantization. That's something we can also do. Maybe that's actually something better to do if you want to just extract like a class association. But here, like we try to figure out like if we can actually scale it. So we're able to scale up to like a 1400 dimensions, which is dyno plus clip. And the reason why we use dyno is because like a clip feature are not very good. It's very like spurious. So we use dyno to actually regularize it, which is the trick from LERF.
Did you try using the unit from implementations? I know Sherry wanted to talk about that last time.
Oh yeah, like I mean, like I feel like you should. Like I'm not like working on that. Yeah, but like it makes sense.
Release.
What's that?
All of this feature splatting and release getting like open source.
Huh?
When will this get open source?
Oh, I mean, like if you just ask me, we can give you access. Let's be avoided. Okay. Yeah, but yeah, so like right now we're trying to like do two things. One thing is that you notice that there's a difference in terms of visualization quality between the feature field paper and the feature splatting paper. That's because it's a lot of effort to actually write like a nice like a visualization pipeline. And very few people like are willing to actually spend time to actually write like a nice like full stack apps. So and I'm on the job market right now, so like it's like I'm just last night I spent like 4 hours like working on like oh actually I want to show you this demo. Like you want to see like a live demo of like feature splatting, sorry, not feature splatting, but like the dolphin splatting running in the browser. So this is like a feature splatting, dolphin splatting running in real time. Yeah. Let me turn off the grid plane. So here's a story.
The reason I was asking about the feature dimension of things, like, do you think you can actually just push the scale up of this feature and get like very semantic queries? Like GPT-4b knows if a drink has caffeine in it or not. I assume the clip plus dyno doesn't, but you could imagine just having some smarter vision language model.
Yes. We'll have a project working on that.
Okay.
So like you can go that's why. So like Andrew Davison has a paper called like a feature realistic field or something like that. So like the main point he was trying to make is before people just kind of try to like save the class labels, which is sparser, lower dimension, and like a cost less memory. And like here, like we really care about like saving the features in an unadulterated form. So for example, like there's a paper that I think came out yesterday. What they did, it's like from Javin's lab, I think. What they did was that they used 3D Gaussians to represent the geometry and the appearance, but then they use a feature field to represent like the features. So you just like query a neural network at each one of the locations. So this is one of the 2 or 3 ways we came up with that like you can do, and the reason why like we choose to actually go directly for the feature splatting, besides that it has a better like a nice name, was that like we want to be able to do physics with it. So that's why. So we want the features to be traveling together with these, and it seems that we figure out like a scalable way to do that. So like in practice, we actually do render a lower dimensional latent feature the same way that these like instant NGP and like a Nexel, like a nerf paper uses a low dimensional like voxel grid as like the like a kind of like sparse explicit representation of the volume. And the primary reason for that is because one, it does make like a training and rendering slightly faster. Actually, I'm not sure about that. Like the primary reason is because we want the dino feature to be regularizing the clip feature so it can get better like 3D segmentation results. Yeah. So like for everyone who's been working on like a feature splatting, like also like other groups who go on this, is that you notice that like the segmentation mask is extremely spotty with these models. Yeah. Cool. Yeah, so this is it's open source, it's called Viewer. It's basically a thin Python like a wrapper for React components. You can use this to build like any like React app, and I can update this 3D scene at like 120 frames per second, while like a beaming in like the 3D point clouds. Like also like this work in VR. So you can just like take this URL and you can actually see animations. So the goal is to use this for all of the data collection. It's open source, so like it's called viewer.ai or viewer-ai on GitHub. Yeah. Questions?
All right, let's thank Go one more time then.